Okay. All right. Let me start over. So in the pre-recorded lecture, we talked about non-parametric tests, and we've been alluding to those, kind of throughout the course when we talk about their parametric counterparts. So all the parametric tests, they make some assumption about the distribution. And in all of the cases that we've discussed, we've been making this assumption about our data being normally distributed. And then there's, for things like correlation, we assume that there's this linear relationship, and all of it, like the t-tests and the ANOVAs, all of those can be tied back into some linear model. And so there is this like linearity assumption, there's normality assumption. And so when those assumptions aren't met, that's when we would then use a non-parametric test. Other times we might use a non-parametric test is, so even if we have like relatively normally distributed data, but we have some outliers, if it's a smallish data set, so like if it's a small data set less than 30, for example, then we might choose to use a non-parametric test because those aren't going to be as influenced by outliers. So if we were to, if we have a relatively small data set, we have some outliers that we want to keep in, then we might choose to do a non-parametric test. If we have a large data set, so like for example, the NHANES data, we had thousands of individuals. Even for like vigorous activity, I think we had like 1,500 individuals for that analysis. That's fairly large. So even if our data weren't, perfectly normally distributed, you could technically still use a parametric test, and that would be okay. But because the vigorous activity had, some extreme outliers and we chose to keep them in, then a non-parametric test is a little bit more appropriate. And then because it's just 2 tests, sometimes it's just good practice to then compare the results with the parametric and the non-parametric pair of tests to see our results. And in most cases we saw last week, right, the results were pretty much the same and our interpretation of those results would have been the same. So our interpretation of the data would not have changed either way. But sometimes that doesn't happen. And I can't remember which specific example we did where the t-test and was it the t-test and what was the other test that we looked at? The one-way ANOVA didn't match up. So, okay, so today we're just going to we're just kind of summarize what was in the pre-recorded lecture, and it's just going into these non-parametric tests in a little bit more detail. Okay, so the first test we talked about was the Wilcoxon rank sum test. Sorry, so that's actually what we ran, not the one-way ANOVA. So it's the non-parametric alternative to the independent samples t-test. So this is when we have a continuous outcome and we want to test differences between 2 conditions in which different participants have used. Or we're looking at 2 independent groups. So for example, in our exercise, we looked at whether there were gender differences in activity, physical activity, and then we also looked at general health. And those are 2 independent groups, right? There's no overlap between those 2 categories of individuals, and so they're independent. And if our normality assumption doesn't hold, or we have small sample sizes, or we have outliers, then we might choose to use a rank sum test instead. And all of these non-parametric tests, at least in this presentation, they're all based on ranked data. Okay, so where it may have been confusing in the pre-recording, like after I recorded it, I realized like it may not have been clear. So I'll hopefully make it a little bit clearer here, where the null hypothesis for all of these tests, they're the same irrespective of the distribution of our data, but the distribution of the data will kind of drive what our alternative hypothesis is. So then what interpretation we make if our p-value is less than 0.05 and we're able to reject the null hypothesis. So What do I mean by different distributions? So here we have identical distributions. So this is a group of males and females, and this is their distribution of engagement score, and they're perfectly overlapped. So not only do they have the same shape, but they have the same scores and values and probably like the same mean, the same median, same variability. They're identical. They're completely overlaid on top of each other. In this case, we have a situation where they actually have a different distribution, right? So the males are skewed left and the females are skewed right. And it looks like the females overall also have, higher scores. They tend to have a higher engagement score. So this shape difference is what we mean by them having a different distribution. So the null hypothesis for the rank sum test is that the distribution of scores for the two groups are equal, right? And most of our null hypotheses, there's some kind of statement about equality or no difference, something like that, right? Or equal to 0. So that's our null hypothesis. If the distributions are different, then the alternative hypothesis is that the distribution of the scores are not equal. So remember, for the t-test, we're actually looking at the mean specifically. For these non-parametric tests, we're just making some broad statement about the distribution. So the distributions are equal, the alternative being the distributions are not equal. So another way of saying this alternative hypothesis is that the mean ranks of the two groups are not equal. So remember, for these non-parametric tests, we convert the scores into a rank, and then we run our analysis on those ranks. And so it's just the mean of those ranks in one group versus the other are not equal. Okay. If we have the same distribution, so in this case, this is exactly the same, right? They completely overlay on top of each other. But in this case, they have the same distribution, they have the same variability, right? So the variance is probably the same between these two, but their central tendency measure, so in this case, the median, because it's skewed, the mean isn't really appropriate, the median is more appropriate. The median is just different. So it's the same shape, but there's just this shift in location. And so the females are just shifted to the right. If the distribution is the same, so they have the same shape, our null hypothesis is still the same as previously. So the distribution of the scores for the two groups are equal. But then we can say, as our alternative hypothesis, that the medians of the two groups are not equal. Okay, so hopefully that makes a little bit more sense.
Okay. I had a quick question on that. Actually, you know what? I could probably just go back and listen to it.
Okay, that's totally fine too. And you can ask here too, either way. Okay, so then we talked about the Wilcoxon signed rank test. So the rank sum test, and then this is the signed rank test. And this is the alternative to a dependent or paired t-test. And so remember, it's similar to the independent samples t-test. So we have a continuous outcome and we're comparing two groups. But this time, the two groups, so the scores come, in those two groups come from the same participants. So it might be something like, we're measuring pre and post. So like in that sprint times example, when individuals took a supplement, we tested their 100-meter sprint time before taking the supplement and after. So those measures are within subject measures, and therefore the data are paired, right? They're somehow correlated because it's coming from the same person. When our assumptions for the paired t-test are not met, then we would choose to use a non-parametric alternative. And so the signed rank test is an alternative to that. And then if you remember, when we say normally distributed, we're referring now, because it's a paired t-test or a paired sample, we're referring to the differences. So not the scores at, say, time point 1 and time point 2, but looking at the difference between those two and then whether that's normally distributed. And then again, like when we have larger and larger sample sizes, these parametric tests are they're okay. They become more okay to use. And I know that's very mushy, but in the case of NHANES having thousands of individuals, it would still be okay to use that parametric test. But because we had, especially in the moderate activity, we had a sizable number of outliers. I think it was 17% of our sample. If we chose to leave those outliers in, then a non-parametric test is more appropriate. Okay, and then if you recall, the paired t-test is the same thing as a one sample t-test. So all the t-tests are comparing a mean to some value. In the one sample t-test, we're looking at the mean and comparing it to some population value. And in this case, the paired t-test is very similar because we're looking at the difference. And then we're just, and here we're saying, the differences are, the difference is 0. So the two groups are the same. And this holds for the signed rank test as well. So, the signed rank test actually has, and I think I didn't go over this in the pre-recorded lecture, I didn't make this clear. The signed rank test, you can do a one sample test, or you can also do a paired, and so I think I've seen it referred to as a paired signed rank test. So you can also do sort of the paired, alternative to this t-test. So again, sorry, maybe that's not clear still. For our t-test, we have a one sample t-test and we have a paired t-test. And those are actually statistically, like mathematically, the same. And that is also the case for the signed rank test. So we can use the signed rank test to do a one sample test, or we can use it to do a paired test. In most cases, you're going to be using it to look at paired data. Okay, so just like the rank sum test, in order to be a test of medians, the distribution of the differences between the two related groups need to be symmetrical in shape. So the null hypothesis here is the median difference between the paired values is equal to 0. So this is different, right, than the rank sum test, and it'll be different from the next test that we'll talk about. And then the alternative is that the median difference between the paired values is not equal to 0. So, So we can refer in this case to the median because we're just looking at one value, right? We're just looking at the difference. We're not actually looking at two groups. But if we're going to state this, then we need to be able to say that the distribution of the differences between the two related groups are symmetrical. It doesn't have to be normal. If it's normal, then we would use a paired t-test, but it would have to be somewhat symmetrical, so not heavily skewed. Okay.
Is that x bar minus x over n equals 0?
Where do you see an x bar? Sorry.
No, nowhere. I'm trying to think of the equation. Like
So for a one sample test, you would have the mu, so it would be population. The population mean equals 0.
Okay.
Yeah, and then if you had a paired test, it would be mu sub d for difference. So it would be, is equal to 0, or you could say mu1 minus mu2 equals 0. Yeah.
Yeah. So okay. Sorry.
Yeah. No problem. Okay, so then the next thing we looked at was the Kruskal-Wallis test. Okay, and that's just the non-parametric counterpart of the one-way independent ANOVA. And remember, the one-way independent ANOVA, you can think of it as kind of like an extension of the independent t-test, right? So the independent t-test, you have two groups. Now with one-way ANOVA, you have 3 or more groups. So you're comparing your continuous or quantitative outcome across 3 or more independent groups. So maybe you're looking at categories of race where you have white, black, Hispanic, and other. So that's 3 or more groups. And so in that case, you would use a one-way independent ANOVA. Oh, sorry. Okay. Yeah, I also like to picture the equation. So I can include those like in future lectures too. If that helps you sort of visualize or conceptualize what's going on with these tests, I'm happy to do that. I've tried to like keep them out because I know that for some folks, like when they, So the important thing is learning the concepts here and then learning how to actually apply them and analyze your data in R. And I know for some folks, like when they start seeing like Greek, so like these mu and like sigma for, standard deviation, their eyes glaze over. So I've tried to, for the most part, kind of avoid that. But if it's helpful for some folks, and it is helpful for me as well, then I'm happy to put those equations back in. And then you can just like ignore them if you want, if it's just more confusing than not. So, okay, so similar to the rank sum test, the null hypothesis is that the distribution of scores for the groups are equal. If the distributions have different shapes, then the alternative hypothesis is that the distribution of scores for at least two groups are not equal. And I think I may have had a typo in the pre-recorded lecture, so I've corrected it, the alternative hypothesis. So it's just similar to the ANOVA. It's like this omnibus test. They're all equal. If you get a statistically significant result, you don't know which two groups are equal, but you know that at least two of them are not equal. So if you have a different shape, that alternative hypothesis is just that at least two groups are not equal. If they have the same shape, then you can say you're comparing the medians. And then if you remember from exercise 2, we actually did a Kruskal-Wallis test. If your p-value is significant, then we would do these post hoc pairwise tests. And the Dunn test is probably one of the more commonly used. And I think I put code in that for exercise 2. Okay, and then the last one, I promise, is Friedman's ANOVA. It's the alternative to a repeated measures ANOVA. So remember, repeated measures, you can think of it like an extension of the paired t-test. So in the paired t-test, you're looking at a continuous outcome across two some within subject factors, so pre and post, for example. In repeated measures, ANOVA, we have 3 or more time points. So, maybe we're measuring individuals at time point 1, 2, 3, 4, and 5. In that case, we would use a repeated measures ANOVA. But if our assumptions don't hold for the ANOVA, like our data is not normally distributed, or it's very skewed, or we have outliers, then we would use a Friedman's ANOVA. So again, this is testing for when we have more than 2 conditions and all the participants are used in all conditions. So we measure something in all participants over time, or maybe we have 3 or more interventions and we have all participants participate in all of those interventions. Okay. So similar to all of the others, the distribution of the scores in each group are equal, or if we have a statistically significant p-value, then we would say the distribution of at least 2 groups differ. So again, if they have different shapes, we're comparing distributions. If they have the same shape, then we can be more specific and say we're comparing the medians. I wonder if I had, okay. Yes, okay, so this is the last slide. So in summary, the parametric tests are appropriate for normally distributed data. And remember, in those paired tests, so a paired t-test or a repeated measures ANOVA, we're talking about the differences, whether the differences are normally distributed, or if we have large samples of non-normally distributed data. So where we have a sample size of 30 or more, or greater than 30. And then we might choose to use a parametric test instead. If we have a small data set or they don't meet the assumptions of our parametric test, or we have outliers that we want to keep in, then a non-parametric test would be more appropriate. And these non-parametric tests are usually based on analyzing the ranked data, not the actual scores. Okay. So these are just the 4 different tests that we talked about. So the rank sum test, the signed rank test, and again, you can have, so it says compares 2 dependent groups because that's most often how you'll use it, but you actually can use it also for a 1 sample test. The Kruskal-Wallis test, that's analogous to the one-way ANOVA, and then the Friedman's test, and that's analogous to the repeated measures ANOVA. Okay, I think that was it. Okay, so I'm gonna open up R. oh, I don't even have it. Okay, I'm gonna open up R on mine. Let's see. Stop share. Okay. So I kind of wanted to pause here maybe and ask, like, do you feel like you're learning, like, do you feel comfortable with R at this point? I know we're a little bit over halfway through the course. Is this sort of method of like going through the exercise together, is that helping? Do you wish that maybe I sort of let you be more independent about coding, or maybe it's not enough detail? I don't know. How are you guys feeling so far about R?
Not that bad. I really like it.
Okay.
As for the like instruction and like really, I mean, in my opinion, it'd be a lot easier if we were like in class. Like
Yeah,
if I had to show me and
that's true. Yeah, I totally agree. It would be, yeah, I wish that we were like in person and, everyone could be like working, let's say, on the exercises during class, like after the lecture itself. And then we can, like I'm able to just sort of like walk around basically, and help you guys. And I know that we can do that virtually, but I'm not tech savvy enough to like try that. So, okay, so I'm glad this is working. And like I said at the start of class, it's like even when I'm coding stuff for work, and even if it's like something that I've done lots and lots of times, a lot of the time, if it's something sort of a little bit like not complicated, but maybe a little bit complicated, like not just a very straightforward statement, for example, I will still go back to like previous code that I've written or Google a procedure to get the syntax for it and the various options, or in R, the analogy for that would be like the different arguments for an R function. Like I'll still go back in and then copy and paste over, like read the documentation if it's something new that I've not used before. So this like idea that all of us are going to be sort of writing code from nothing without referring to anything I don't think it's realistic. I don't think it even happens in the real world. So it probably does for like super amazing coders. I would put like severe in that bin, but like for myself and probably most people, like I still have to go back and like reference things when I'm writing like a new program. So okay, so I'm glad this is working so far. Let me open up. Okay, right. I've been talking, so I haven't like opened up R. So I'm going to open up R and then share my screen. Was everyone able to at least download the data sets? I think we're using weight management and the strength data today. So I just want to make sure everybody has the data sets. You're able to download them. Okay, awesome. And then I should have asked if you could like install the data sets beforehand, but it'll be really quick and they're SAV files. I have R open and I'm not sure why it's not showing up on my share screen options. Hold on one second. Okay. Interesting. Okay, hold on one second. Okay, now it's showing up. That's really weird. Okay, so can everyone see my R screen?
Yeah.
Okay, awesome. And as you can see, I was doing this last night, so that's 10-10. Do not recommend doing that. So yeah, okay. So the first thing I'm going to do is pull in, I'm going to set my working directory. So remember, you guys can do that from here as well. So go ahead and set your working directory if you haven't already, and you can do that more interactively here. but I'm gonna run mine. Okay. The other thing is these are the different packages actually that you need for the entire exercise. We don't need all of them today, but I'm just gonna like send them to you guys anyway. And chat. I'm having a lot of like technical issues today. I can't, oh, okay, there. All right. Okay. Do you guys have that code in your chat? So you should all be able to run these. So go ahead and load those packages. Okay, so they all, okay. All right. Was everyone able to run those, load those packages?
No, they weren't in the chat.
Oh. Wait, do you want me to copy and paste these again? Sorry, into the chat?
Yes, please.
Okay. That's so weird. Oh my gosh. Okay. I almost feel like, okay, let's just stop and like we'll start over. I'm having so many technical issues. Oh, I got it. All right. So I've been sending this to the waiting room, and that is why. All right. I apologize. Definitely off my game this morning. Okay. All right. So, all right. Was everyone able to run those?
Not yet.
Okay. Okay, let me know if you guys have loaded those packages or if you still need more time. Okay. Okay. So we're gonna go ahead. Question one, I just wrote the actual question into the program, so I don't have to like toggle back and forth between R and Word. A sports scientist wanted to investigate the progress of his athletes in gaining muscular strength during a 4-week weight training program. So 8 athletes participated in the training program aimed at improving their muscular strength. And then their strength was measured at baseline, 2 weeks, and after 4 weeks. And then the question is, was there a difference in muscular strength in the training program? So given this information, what test do you think we should use? So we have a continuous outcome, and we have 3 time points, and that's a within subject measure, right? So we're measuring everybody at baseline, at 2 weeks, and then at 4 weeks. Okay, so paired t-test is close. So we have more than 2 time points. And because we have more than 2 time points, then we need to use some kind of ANOVA, right? And because it's a within subject measure, we need to use a repeated measures ANOVA. Okay, perfect. That's great, Amanda. Okay, so if we do conduct a repeated measures ANOVA, then we'll want to check the following assumptions. Okay, so remember, because they're repeated measures, so we're looking at, this is paired data, the observations are defined as differences between the sets of values, right? So when we say the distribution of our independent variables or the observations need to be normally distributed in order to meet one of the assumptions for the repeated measures ANOVA, we're actually referring to the differences between each pair. So the difference between baseline and 2 weeks, baseline and 4 weeks, and 2 weeks and 4 weeks. So just like with the paired t-test, we're talking about differences. The same thing, it's the same thing with the repeated measures ANOVA. Okay. Okay. So the assumptions are that with our data are, so the differences are approximately normally distributed. ANOVA is pretty robust. So even if our data are like kind of normally distributed, you know, they're not super skewed, or there's like really extreme outliers, we can actually still use ANOVA. So it's pretty, like when we say robust, it's like resistant to these violations of these assumptions. So you'll find, I know we've been very kind of strict about checking our assumptions and making sure we meet them before running a test. And we still want to do that in the real world, like when you're working on your thesis, or if you continue on and do your own research, you still want to check those assumptions. You still want to do diagnostic tests after you run your analyses to make sure that you've met some of those assumptions. But there are certain assumptions that you can violate. Sounds awful, but you can violate, like you don't really meet those assumptions perfectly, and it's still okay to use those tests. And so, you know, again, this is where like statistics, like the mathematical portion of it, probability theory, those are all like real and true, and they're not going to change. There really is like a right or wrong when you're solving an equation, for example, right? But when we start to talk about methods and methodology and what are the appropriate analyses for a particular research problem, it can get kind of mushy. So some people might, you know, be very comfortable running an ANOVA if you know, let's say if your data are not like perfectly normally distributed or very close. And then others might be more comfortable sort of relaxing a little bit and saying, okay, maybe they're not, you know, perfectly normally distributed, but I don't have any outliers. It's still kind of somewhat, you know, it's close to a normal distribution, so I'm going to use this parametric test anyway. And so this is where everything gets a little bit mushy. Fortunately, I think if I recall correctly, we actually do meet all of these assumptions, so we're good here. And the ANOVA, the repeated measures ANOVA is appropriate. Okay, so there's that normally distributed, and again, that's the differences are normally distributed. We also want to check for outliers. And then this repeated measures ANOVA also has this additional assumption of sphericity. And that just means that the variability in each like possible pair is the same. So it's very similar to this like homogeneity of variances for our paired t-test. It's very similar, it's just extending now to more than 2 groups. So that's that like weird like homoscedasticity term. But in this case, it's just more than 2 groups now. The nice thing is the ANOVA test function, which we'll use to run the repeated measures, that will actually give you the results of that test. And we use this Moschli's test for that. So it will automatically check for you and then give you an adjusted p-value if you don't meet that assumption. So if these assumptions are not met, so let's say we have very skewed data, or we have extreme outliers, then we would use Friedman's ANOVA. If this assumption of sphericity is not met, we actually can just make an adjustment to the degrees of freedom, and then that sort of but it adjusts the F statistic, and then we can use that sort of adjusted value and then interpret that p-value instead. Okay, so the first thing we're going to do is read in the data set. Either you can go here, so in this lower right corner, right, I have all of my data sets here, and then you can just click on the strength data and import data set. So you can do that, and then just copy that code if you want, or you can just import it. I would change that to strength. So you can do that. So that's one option, or you can just read it in here. And then I have, right, this is the folder where I include my data sets. I'm already in my working directory. And so all I need to do is put data sets and then the data set name. And this happens to be, I think, an SPSS file. So I'm going to copy and paste that here. Oh, okay. You're still in a zip file. Okay, so I'm going to drop. One second. Okay. Okay. So I'm dropping that data into the chat. You should be able to just save that individual data set. And then I'm going to do the same thing with the weight management data set, since we're going to use that too. Okay. All right, so April, let me know if that helps, if that works. You can just sort of download it from the chat. Okay, so let me know if you have now your strength data set. Okay, awesome, April. Okay, was everyone able to import the data set into R? Okay, awesome. I'm gonna run my code, and then I have this view strength. So what's one thing you notice about this data set? So we've talked about in the past, when you have a data set and we have, like, you know, our individuals in the data set, we almost always, I can't think of an instance where we wouldn't want to have some kind of identifier for them, right? So some kind of subject ID or ID number, because if I were to look at these data, I want to tie it back in to an individual. And if I were to just look at this, I wouldn't be able to do that, right? These are just, it's basically just the variables that I'm going to be using for the analysis, but I don't have any variable to sort of tie them back to a specific individual. And that can be problematic for, you know, it's actually a problem for this particular analysis, but it's also sort of just, it's not really good data to, you know, to not be able to do that, to tie it back to an individual. So even in the case of, like, let's say de-identified data, for example, we still want some kind of indicator where we can group all of these different observations to a single person. So the first thing we're going to do, and that was my question, like, what do you notice about the strength data? So we're going to add the ID number to the data set. So in this case, so I know, like, I've sort of like really pushed, like, anytime you make a modification to the data set, you should change the data set name. In this case, we're just adding a column, and we're adding the column with ID and then giving them, like, sequential numbers. So I would say, like, it's okay if we just keep the same object name. So this is still strength. And then Tibble is just like, it's just a data frame. And then we're saying, you know, add these IDs as a column to this data set. And then we're calling that new column, that new variable ID. So I'm going to copy and paste that. Okay. So go ahead and run that code, and then we'll open up the strength data set and look at it after we've run that code. So now that we've done that, you can see it's added this variable or this column called ID, and then it's just given this a sequential number. Okay. So that's awesome. And now we have that. Okay. And then, okay. So the first thing that we'll do is we'll check our assumptions for the repeated measures ANOVA. And remember, when we're talking about normality and outliers, we're looking at the differences. So the first thing I did was create different variables or values for each of the pairs. In this case, we can just do it one by one because we only have 3 time points. So there's only three possible pairs. If we had lots and lots of time points, then this is not the way to go. I would have to look into how to do this in R sort of iteratively. In the programming language that I use, we would use an array of some sort. But here we can just hard code. So let me just copy and paste. So here I'm creating an object called sDifference1, sDifference2, and I put S here to denote the difference for the strength data, and then just taking the difference between each possible pair. So 4 weeks versus the baseline, 2 weeks versus baseline, and then 4 weeks minus 2 weeks. So I'm going to also share that. Oh, sorry. The name of my data set is strength. So it's just that, and it's all lowercase. Okay, so I'm gonna go ahead and run this.
Oh, sorry. I was responding to April and Alex.
Oh, okay.
Because I was just gonna say I changed the name of my data set, or
okay, gotcha.
I think I had the same issue, so that's what I just changed it to whatever mine was called. So.
Oh, okay. Oh, okay.
So
right.
yeah, I was also having the same issue, and I'm still kind of trying to figure out what it's saved in in my computer. So I'm
So
I'm a couple steps behind right now.
Okay, so if you imported the data set, okay, so I guess question, did you guys import the data set just clicking on this and import data?
Yeah, that's how I did mine.
Okay, so when you do that, the name of the object that it creates is strength data. So that's the name of, so you can also see it here in the code. So that's the name of your object, your R object now. So you can either, and this might be the easiest thing because as I copy and paste all the code, so if you can see here, right, my object name is strength. So when I refer to the data set, it's going to be strength, not strength data. So I would recommend importing the data set and then just changing this in the bottom left corner here to strength. And then once you do that, you should be able to import it, and then you see the code even changed here. So go ahead and do that, and then you should also see here in the upper right corner in your global environment, the name of your data sets. And here you have strength. If you kept that code where it's names it strength data, and it by default, R is going to call it strength data because that's the name of the original data set, then you would have to go in and you would just change this, which is totally fine. You can name your data set whatever you want. But that's what you would need to do. You would need to change it to strength data with a capital S and a capital D, and then all of this should work. Same thing here. So, but for efficiency or more ease going through it, so you don't have to modify the code that I send through the chat, I would recommend just changing it to strength. So let me know if that works. I think it's Alex and April. And for some reason, I can't see. Okay. Oh, okay. Sorry. Okay. Okay, wait. Okay, so your data set, so April, Alex, your data set's only showing one variable. So here. Okay. Can you try downloading the data set that I attached to the chat and see if you can save it? Okay, you did. Okay, I'm gonna have you share your screen. Let's see. Okay. So you're a co-host now, so if you want, you can go ahead and share your screen.
Yeah, I don't know what happened. I just have like one variable for each of my data sets. But yet I tried downloading it from Cougar Courses, and then I tried downloading it from your group chat, but then it just came out as one variable. So I'm confused at what I'm doing wrong.
Okay, so in your bottom right corner, if you, okay, hold on one second. Sorry, I'm just reading your console.
No, yeah.
Okay. Okay, so it's actually, there's like some issue reading it in. So if you were to like click on any of those data sets, it's probably blank.
Yeah, it says non-app.
Yeah, there's like
NA.
NA. Yeah,
Yeah.
exactly. Okay, so in the bottom right corner, go ahead and click on Files.
Okay.
And then,
Look for it there.
yeah.
Where it chooses to load. Oh gosh.
So it would be strength data.
Uh-huh. Yeah, I saved it to my desktop, so I'm like wondering where it would be in here.
Oh, okay. Okay, scroll back up maybe.
I'm like, where's 2020? I'm like, where? Okay. Do I have it? Nope, that just went away. Oh my gosh.
So one thing you could do is go to your desktop and copy and paste your data set into like a different folder. Not sure if that will make a difference, but it's worth a try. So we can like save it to like your C drive or something like that.
So like go into it and then try saving it into like,
Yeah.
okay. What's into work? Oh, maybe documents. Let's see.
Oh yeah, that would be a fine place too.
Yeah, just at least for now, so I'm not taking up too much time.
It's totally fine. We're actually going to go just through like these 2 questions and we'll probably still finish early.
Okay. Because I hate that I'm always the one that's like making everybody.
It's totally fine. It's totally fine. Like I'm so grateful that this is like a smaller class too, because I feel like we have a lot more flexibility that way. So
Let's try those again. Hopefully it's more. Okay, there's strength data.
okay, so great. Okay, so click on that. You can actually just click on it on strength data.
Okay.
Mm-hmm.
And then,
Import data set. Yep.
okay.
Awesome.
Is it going? Okay, good.
Okay. And then you see in the lower left-hand corner, in the lower left-hand corner in the name, that box that says name and import, no, so on the left side under import options,
Oh, yeah, this, so
go ahead and change that to strength in all lowercase letters. And then that will actually change the code preview. Yep. And then you can just hit import. Perfect.
Okay, well now I have the data set.
Awesome. Okay, so now what you'll want to do is run that line of code that adds the ID number to it.
Okay, so was it this?
So go ahead and run that line of code.
Okay.
And then, right, now you see how it changed from 3 variables to 4. So now you have the ID variable in there, and now you should be good to go for all the rest of the code, including the 3 lines 10, 11, and 12. So you should be able to run that now too.
All right, awesome. Thank you so much.
Okay, awesome. No problem. Okay, let me go back to sharing my screen. Okay. All right. And then maybe make sure I can see the chat. Okay, awesome. Okay, so I ran and created these differences values. And then now that I have those differences, I'm just going to run the Shapiro-Wilk test. And remember, that's the test for normality. So the null hypothesis is that the distribution is normal. So I'm going to copy and paste those into the chat. Okay. Once you've run that, I'll kind of direct your attention to the console. So for all of these Shapiro-Wilk tests, the p-values are all greater than 0.05. So what would we, like, how would we interpret these results? And then what conclusion would we make based on those results? So the null hypothesis is that the distribution is normal and the p-value is greater than 0.05. So we fail to reject the null hypothesis. And so therefore we conclude that the distribution is normal for each of these differences, which is great, right? That's what we want. So it's kind of funny, right? Typically, in our research, we want p-values less than 0.05. This is one of those instances where we want it to be, we want it to be a non-significant result. So we've met that normality assumption. Okay, the second thing that we're gonna do is run these box plots and we can look to see if we have any outliers. And again, there are different ways to do this, right? We can do a box plot with a capital B that will let us know if there are outliers and tell us who those outliers are. They'll give the observation number. So again, important reason why we have ID number. And then, you could also use like an outlier. I can't remember off the top of my head, but there's a function to just pull out the outliers and then R will display those as well. I'm more visual. So I think having these box plots, for me, that's what works for me. So go ahead and run those one at a time. So we'll run it on the first difference value. Okay, and then you can see here we don't have any outliers, right? If we did, there would be like little dots up here or down here. So that's great. And then we can run the second box plot. And then again, we don't have any outliers. And then go ahead and run the third one. And same thing. Okay. Okay. So for the normality assumption, for the outliers, we've met those assumptions. Again, when we actually run the repeated measures ANOVA, that function will test this assumption of sphericity. And then we'll take a look at the results and then I'll kind of go over what you need to look at when you run your repeated measures ANOVA. Okay, so the first thing, I think if you recall from exercise 1, we ran I think it was for a paired t-test. So there are different ways to do the same thing. And this is true for almost all programming languages. And this is definitely true for R, especially because it's open source and people can write like their own packages and everything like that, and then sort of like publish it to R and make it available for everybody. So hence, we have this box plot function with a capital B. Base SAS also has a box plot function with a lowercase b, and that will tell you if you have outliers. It'll have like these dots, but it won't give you the ID number or the observation number, so you wouldn't be able to like identify them visually, which is why I prefer this box plot function with a capital B. So the same thing, like even with something like the paired t-test, you can run it in different ways. There are different functions that you can use. In this particular case, for this repeated measures ANOVA, Sorry, so where I was going with that is sometimes we need our data to be wide and sometimes we need it to be long for these different functions. And in this case, so I'm going to click on the strength data and just show you. So remember, a wide data set, we have these 3 time points, right? Baseline, 2 weeks, and 4 weeks. For a wide data set, it just means that those are in the columns. And so we have 1 row per individual. So for example, this is individual 1, and then we have their 3 different time points as columns. If it was a long file, then we would have 3 rows per person, right? So we would have person 1, time point 1, person 1, time point 2, person 1, time point 3. So that would be a long file. Okay, so I'm going to go back. For this ANOVA test function, we do need to have our data in long form. So I'm going to copy and paste this into the chat, and then I'll kind of explain what it's doing. Okay, so here we're creating a new data set and we're calling it strength long. And then we're taking our original data set. And then remember, this is like that pipe operator. So we could run each of these functions separately. So we could do like gather this, create a new data set, take that new data set, then run it through this function, take that new data set, then run it through this function. Instead of doing it piecemeal that way, we can use this pipe operator. So it basically just passes on the result. So it's passing strength on into this function, and then it's passing the result from that here with this pipe operator into this function. And then now we're just showing, I think, strength up to like 50 observations. So go ahead and run that. I'm going to run it here too. So it's basically saying, okay, what variables do I need to take and shift into long? And I'm sort of just imagining like if you have your arm up like horizontally and let it fall vertically, that's kind of what it's doing. And then you're converting these to factors. Okay, once you run that code, you should have this data set here called strength long. I'm going to click on that so you can see what I mean by long data set. Okay, so now, okay, so this is weird. R has actually sort of sorted it differently. So it's not actually sorted by individual, but you still have multiple rows per individual. So let's say person 1, this is their strength, muscular strength measure for baseline. Okay, and then in the second measure for individual 1 just happens to be down here. Usually we would sort by ID. So typically you'll see data sets with like person 1, person 1, person 1, person 2, person 2, person 2. R just happens to do it this way, and then you can, if you need to, then go ahead and sort it. But here is individual 1 for their muscular strength measure at week 2. And then,
so I just clicked on the ID where there's the ID box where there's the little arrows. I just clicked that.
Oh, and you can sort
sorted
it. Yeah. Okay, awesome. So that's like something that I didn't know about R. It's like way more interactive than the program that I use. Like for the program that I use, we would have to sort it like with a line of code. So this is great. We don't actually need to sort it in this case, but this is really nice, right? Where you can see each group of individuals or each individual has 3 rows corresponding to the 3 different time points. Okay, awesome. Okay, so now we're actually going to run the repeated measures ANOVA. So the function is ANOVA test. You're telling R what your data set name is. It's condition. So let me go back and, okay, so right, this is condition. This is just the variable name for the muscular strength measure. So that's our dependent variable. Our within ID, so again, and this is highlights why it's important to have an ID number. So basically this is indicating to R what our by group is. So or like what ties like an individual together, what identifies a single individual. And so this is our within subject ID number. And then we're saying, okay, the repeated measures like factor is time. And then let me kind of go back. So you can see like that variable name is time. Okay, so let me copy and paste this. And then I'll run it myself. Okay, so remember, sphericity is similar to this idea of homogeneity of variances or homoscedasticity, where the variances like are generally like the same across all values in a group. So in this case, it's we're looking at the differences, the variance of the differences between all pairs, so all combinations of related groups. And we're saying the assumption is that these are all equal. We would use Moschli's test to test this. And the nice thing about this ANOVA test function is that it does that for us. So if you look here in the console area, you'll notice that, so this is the results of the repeated measures ANOVA test. And it gives us an F statistic and then our p-value. So our p-value is less than 0.05. Okay, so our inclination is to then say, okay, this is a statistically significant result. That means that at least two of these groups are different, or there's at least one pair that's different than the others. But the first thing so let me backtrack. The first thing we should do is look at the results for this test for sphericity. Okay, so remember the null hypothesis is that the variances are all the same. And if we reject that, then we would say like at least one is different. One set of variances is different. In this case, our p-value is greater than 0.05, so we fail to reject that null hypothesis. So we fail to reject the null hypothesis that the variance of the differences are equal, which is actually what we want. Because if they're not, then we need to make this adjustment, right? And the adjustment is actually making an adjustment. It's decreasing the degrees of freedom, and that produces a valid F statistic and then this sort of adjusted p-value. So because this is not statistically significant, because it's greater than 0.05, we can use this result here. So we can actually use this p-value to make our inference. So in this case, it's greater than 0.05, so we fail to reject that null hypothesis that the variance of the differences are equal. So we can then use this p-value. So this p-value is less than 0.05. And remember, the null hypothesis for the repeated measures ANOVA is that all the groups are also like the means for all the groups are the same. Since we reject that null hypothesis, we know that at least one of those is different. At least one pair is different. Okay, let me just give you an instance. If this is less than 0.05, then we would want to go down and look at this p-value. So this adjusted p-value. Because that assumption is met, the p-values are actually the same. Pretty similar. Okay. Hopefully that all makes sense. Because we met the assumption for sphericity, because our p-value is greater than 0.05, we can use the p-value up here. So now, because we have a significant test result for this repeated measures ANOVA, we have to then go and run post hoc tests to see which pair is actually different. So we don't know whether the difference is between baseline in week 2, baseline in week 4, or week 2 and week 4. We don't know which one is different. So that's where we go ahead and run these post hoc tests. Okay, so let me just scroll down. Okay. So for these post hoc tests, we can just run pairwise paired t-tests. So we're going to run paired t-tests for time 0 versus time 2 or 2 weeks, time 0 versus 4 weeks, and then 2 weeks versus 4 weeks. So those are all paired t-tests, and that's the post hoc test that we're going to run. So I'm going to go ahead and copy and paste that code. So we're creating this object post hoc that's going to hold all of our results for these paired t-tests. And then this is just running the paired t-test for each possible pair. And then because we have such a small sample, so we only have 3 pairs that we're comparing, we can make like a Bonferroni adjustment. If we had like hundreds of paired t-tests to run, then Bonferroni is probably going to be overly conservative and you might want to pick another kind of adjustment. So like maybe like Benjamini and Hochberg. Again, you can just write p.adjust.method and that'll give you the different adjustment methods that you'll want. But because we have just 3 pairs to compare to look at, Bonferroni is fine. Okay, so I'm going to run that. Okay. All right, so this gives us the result of each paired t-test. So this is looking at 4 weeks versus 2 weeks. Okay, and our adjusted p-value for that is 0.089. So it's greater than 0.05. So those 2 groups are not, that's not where our difference was. I also want to point you to this. So if you look at just the p-value, it's actually significant, right? It's less than 0.05. So this is a great illustration of why it's important to make these adjustments for multiple testing. Because once we've made that adjustment, that p-value is no longer significant. So again, Bonferroni is correcting for the fact that we're making these multiple adjustments. It's actually taking the p-value and dividing it by 3 because we have 3 different tests that we're conducting. And so the result is 0.089, and it's not significant. Okay. For week 4 versus baseline, when we look at the adjusted p-value, it's less than 0.05, so it is significant. So we know that at least that pair is different, and that's one of the things that's driving this, or I'm sorry, let me scroll up and highlight the correct p-value, this p-value here. Okay, and then for our last paired comparison, we're looking at 2 weeks versus baseline. And you can see that p-value is 0.348. So that's greater than 0.05, so it's not significant. So what we can say, like if you were to run a study like this, you would run your repeated measures ANOVA. You would give the results of that, that repeated measures ANOVA. You would probably also want to report like all assumptions were met, including the assumption of sphericity. We had a statistically significant result. So there is a difference, before and after this strength training program, we had a p-value of 0.003. So you could report it that way. And then we conducted pairwise paired t-tests as your post hoc tests. And the result of that was we found that there was a statistically significant difference in strength between baseline and 4 weeks. So that's how you would want to report your results.
Question.
Mm-hmm.
Why, so since the post hoc gave us the specific about the baseline and 4 week, then why would we need to run the original repeated measure ANOVA?
So that's actually a really, really good question. So the reason being is that, okay, so there are 2 things going on. The repeated measures ANOVA is this omnibus test. It's just testing for if there are any differences, right, across all of the different possible pairs. And because it conducts it in one single test, it's actually a lot more statistically powerful. And if we were to just run that repeated measures test and get a non-significant result, so let's say our p-value is like 0.3 instead of 0.003, then we would conclude that that all of the groups were the same. So there were no differences across the groups, and we would just stop there. And we would have no need for these post hoc tests. So it's really only the case if we have a statistically significant result from that repeated measures ANOVA that we would then need to run these post hoc tests. And then the other thing is so in this case, it kind of makes sense, right? That the one statistically significant result is between baseline and 4 weeks, because we would assume that if the strength training program does work, that, maybe it takes a little bit of time, and, 2 weeks may not be enough time. And so our greatest difference will be between baseline and 4 weeks. So this is actually not a very surprising result. Let's say we had a case where maybe we had, 10 different time points. And, instead of running like all different possible, pair comparisons for those 10 different time points, it would be a lot easier and a lot quicker, right? Just running a single repeated measures ANOVA and only having to do those pairwise tests if we had a significant result for the ANOVA. So that's one reason. And then the other reason is, we can, let's say we run the repeated measures ANOVA and we have like an idea of, let me just think this out in my head before I actually speak it out loud. Okay, never mind. I think, so where I was going is probably just going to be more confusing, but I do want to add that, and I know we talked about it a little bit in lecture, sometimes we have these like planned comparisons, right? So this is now sort of only tangential to your question, so sorry, Alex, but so that answers your question. And then just one other note that I want to make is sometimes, let's say we do have 10 different time points. And, we really only are interested in, time point 0 versus, the very last time point. And we think that that's where the biggest difference is going to be. Or maybe we think the biggest differences occur early on in the study and not so much later. So maybe we only want to compare time point, 1 versus time point 2, time point 1 versus time point 3, and then time point 1 versus time point 10, something like that. So just an example where we only want to conduct like a certain number of paired comparisons if we get a statistically significant result from our repeated measures ANOVA. That would be also a more sort of like statistically efficient way to handle this instead of running like all different paired comparisons. So that's kind of more talking about like a planned comparisons versus just sort of agnostic post hoc tests. But so to go back to your question, again, it's more statistically, like it's more powerful to have this like single omnibus test, so the repeated measures ANOVA, rather than running all these different pairwise tests, especially if we have like lots and lots of time points. So in this case, we only had 3 paired comparisons, but you can imagine if we had like 10 time points, that's a lot of paired comparisons to make. And it might be a waste of time if we were to run our repeated measures ANOVA and get a non-statistically significant result, because that would just tell us, okay, that's it, we can stop right there. There are no differences. So hopefully that helps. Okay, let's try time. Okay. All right, so we're going to move on to question 2, and that actually requires a different data set. So what's question 2? 15 women participated in an 8-week weight management program. Their weights were measured before and after the program. It's in the data set weight management. Is there a difference in the women's weight before and after the weight management program? And then we would describe our findings. It asks us to describe our findings in a sentence by comparing the means, so the mean values of their weights. So we have a continuous outcome, and we have 2 time points. We're measuring their weight before and after a weight loss program, right? So that's a within subject measure. So what test would we use in this case? Sorry, I just drank water. Okay, so in this case, we would use a paired t-test, right? Because we just have 2 time points. So anytime it's like 2, we can think, okay, t-test or some alternative to those t-tests. So the rank sum test and the signed rank test. If we have 3 or more levels in our factor, so whether it's time or it's something independent like race, then we would use an ANOVA, some form of ANOVA, whether it's a one-way ANOVA or a repeated measures ANOVA. So in this case, we have 2 time points and it's a within subject measure, so it's paired, and we have a continuous outcome, so we can use a paired t-test. Okay, so go ahead and import your data. So you can either use, like, I'll copy and paste the code. You can either use that code, or you can go into the lower right corner here, and then click on weight management, import data set, and then just change this to weight, all lowercase. And then let me actually, I attached it above, but let me just attach it again, just in case you need to download it. Okay. So let me know when you've imported that weight management data set. Okay, awesome. All right, so what I'm gonna do is, so for the paired t-test, you may or may not remember like the code, the syntax for that. We actually don't need an ID number, but I'm adding one anyway. I think it's just good practice to have this, ID number where you can tie back into an individual. Okay, so go ahead and run that code. Interesting. Okay, so I actually need to run this. No wonder. Okay, I was like, where is my data set? It's here. I just didn't run the code. All right. Oh, interesting. Okay. Wait, sorry. Okay, that's why. All right. Sorry, I ran it twice, and so it was saying I can't create another column with the same variable name. Okay. So you guys should now have a data set that looks like this, where you have your ID variable, pre-program weight, and post-program weight. And the variable names for that are pre-weight and post-weight. Okay. So again, we need to test for normality and outliers, and because it's
I have a question.
Oh yeah, sure.
So is there a way to rename it once it's already been imported?
Like here?
Yeah, because I already did like import data set and selected it and input it. So
Okay, what's your data set name?
it's the original one, which is weight_management.
Okay, so this is probably the easiest. I'm just there. It's creating another object called weight from weight management. So they're basically going to be like duplicate data sets. Yeah. I'm sure there's a better way to do this without creating a completely like new data set, but that should work. So that's like my patch, my Band-Aid. Did that work?
Sorry, I'm still I have to always toggle over, so it always takes me a little bit.
Oh yeah, no worries. Yeah, I think for me, like it's okay if your data set name is like the original or whatever R defaults to. That's totally fine. You just need to like make adjustments here when we refer to the data set. It's just my preference to have like as short as possible data set name, as well as all lowercase, or you could do it like all uppercase, just because like the mixed case is, just because R is case sensitive, I don't like using mixed case for at least things that I can create. But okay.
Okay, yeah, that worked.
Okay, awesome. All right. So remember when we're talking about normality and outliers, because it's paired data, we're talking about the differences. So those are our observations. It's actually the differences, not the actual scores or the original data values. So in this case, it would be the differences in the weight values, pre and post, not the actual weight values themselves. So I'm going to create a difference variable. And then again, like I have W here just to indicate like it's coming from the weight data set. And then I'm just taking the difference between post program and the pre-program weight. So I'm going to copy and paste that for you guys here and then run that myself. Okay. And then you should see here, it's kind of cool. Like R gives you sort of a preview of the different values for the, in that little like vector. Okay. So now that we have the differences, oh, and okay. All right. This is what happens when you do things late at night and you're really tired. Like I didn't even do the test for normality and outliers with that. So go ahead and do that. Okay. Nice. So our Shapiro-Wilk test, so testing for normality, we have a p-value that's greater than 0.05. So we fail to reject the null hypothesis that the data are normally distributed, so that the differences are normally distributed. That's what we want. That's great. So we've met that assumption of normality. Okay. And then I think, oops, sorry. Nope, it's just one object. Okay. Let me copy and paste that for you guys. And then go ahead and run your box plot. And I'm just going to cross my fingers. Okay, great. No outliers. If there was an outlier, it's a small data set. It's 15 people. Removing it, it's like, it would depend probably on the value of that outlier. If it was very, very extreme, like a very extreme difference, like someone lost like 40 pounds or something like that, whereas everyone else lost between like, you know, no weight and 12 pounds, then I might choose to remove that person or leave them in and do a non-parametric test. So instead of the paired t-test, then I would run like a signed rank test. But we don't have any outliers, and it looks like the differences, the values of the differences are normally distributed, so that's great. So we're good to go with a paired t-test. Okay, so the code for that is a t-test. Remember, for the paired t-test, we put our post-program weight first. It actually, so we'll run it both ways, and we did this with exercise 1, but I'll just show you again what that looks like. So first, let me just copy and paste this. Okay, let me just copy and paste this code first. Okay, so you can go ahead and run it. And then while you're doing that, I'm going to modify this code and just show you what I mean by the order of the variables. So, okay. All right, so go ahead and run that chunk of code that I sent you through the chat. All right, so you can see that the p-value is, excuse me, quite small, or it's less than 0.05. The null hypothesis is that like there's no difference, right? And then the alternative is that the difference is not equal to 0, so that there is a difference between the pre and post weight. And then you can see that the mean of the differences is negative 5.2. So there is a significant change in weight and it's negative, right? So people lost weight on this program. Okay, and you can even see like when we calculated the differences, these values are all negative, and you can see in our box plot too, where, you know, for most people, it looks like maybe one person gained maybe like a pound, and that, you know, that person is out here, but everybody else either, you know, did not gain any weight at all, or so there was no weight change, but most people actually lost weight, right? So when we created that variable here, we took, oh, thank you. We took the post-program weight minus the pre-program weight, and most people actually lost weight. If we were to run the paired t-test, and let's say we accidentally put the pre-weight first, this is what would happen. So I'm just gonna run it to show you. So I'm not gonna send it to you because you don't need to run it. Our p-value is the same, right? Our t statistic, everything is the same, except it's negative now, right? So the t statistic is negative up here. The p-value is the same, right? The magnitude or the absolute value of the t statistic is also the same. Okay. But if you look here, right, the confidence interval for our mean of the differences is flipped. And then the mean and differences is actually positive. So so if we were to just rely on this and then accidentally like put pre-weight first and then post-weight, you know, we might come to like the wrong, not conclusion, because we would say, yes, there's a difference, but we would come to the wrong like conclusion in terms of the direction of the difference or the change, the actual change. So this is where it's good. The question does ask us to look at the means and make a statement, like just a one-sentence statement about our results, given the means, and then our result from the paired t-test. So I'm gonna send that to you. Oh, sorry. Don't run that. You're gonna need to do this. Okay, sorry. Ignore that first code up here in the chat. Go ahead and run it with the actual like data set name in front of it. Okay, so our mean weight before the weight loss program is about 156 pounds. And then after the weight loss program, the average weight for the 15 women was 150 pounds. So given that, what's basically a one-sentence statement that we can make about these results? And if you'll notice, like the difference is 5.2, right? Let's see. Let me look up here. Was it an 8-week program? Exactly. So, and we can be even more detailed about that, right? So we can say after an 8-week weight management program, there was a statistically significant change or a statistically significant weight loss, you know, and on average, you know, women lost 5.2 pounds. So, you know, on average, women lost, you know, 5 pounds after this 8-week management program, weight management program, and there was this, you know, statistically significant. This finding was statistically significant, and then you could put in parentheses your p-value, and that p-value is like very, very small, so you could just say less than 0.001, for example. Okay, so I'm going to actually stop there, and we can do questions 3 and 4 next week. But I'll pause to see if anybody has any questions about question 1 or question 2 for this exercise. Okay, so all right, so if there are no questions, then we'll stop here. Next week's lecture, and I apologize because I recorded the lecture on Friday and I didn't upload it till Saturday. So I apologize for that. So I will upload it Friday night. We're going to be talking about categorical data analysis. I initially had wanted to combine the two, so non-parametric and then getting categorical analysis together, because we started to actually do some of that in our exercises, or at least see results of categorical data analysis. So like the chi-square test, for example, in table 1. But as I was like putting the lecture together, I think it was too much to combine. I felt like, and they're very like sort of distinct topics. So this week's lecture will also be quite short. We're going to talk about categorical data analysis, and that includes different, like a statistical test, so chi-square tests, and then logistic regression. And that's just, it's like linear regression, except we have a binary outcome. So we'll talk about that too. And then we'll just continue with exercise 3 on Tuesday after like a brief like summary lecture for those topics. So that's all I had for today. And then if you still have like a month, so you still have quite a bit of time, but if you haven't already, oh shoot, you're right, it's spring break. Okay, sorry, my older son, his spring break is the week after yours, so I keep thinking it's the 2 weeks from now. So, okay, awesome. So we're gonna break here, and then we will resume in 2 weeks. I'll probably still try to post the lecture and all that on Friday, and then 2 weeks from now on Tuesday, we'll have a summary lecture for categorical data analysis, and then we'll probably end up completing exercise 3. And then what was the only other thing? Okay, yes, we still have a month, so you definitely have time. But if you haven't already, start to think about the research question that you want to use for your final project, and look at different data sets that are publicly available, or if you have one for your thesis, you can use that as well, even if it's not like a complete data set. So I know at least one student has partial data collection for your thesis. If you want, you can just use that for your final project, even knowing that you'll continue to collect additional individuals for your actual thesis. So that's totally fine too. But okay, and I am actually around the whole time, so if you have any questions in the meantime, please feel free to email me. And I will also hold office hours this Friday. Thank you. Thank you for reminding me. Otherwise, I would have shown up on Tuesday. All right.
I was wondering if I would be able to stay and talk to you about I guess a bunch of stuff, but my research question, I guess.
Oh yeah, totally. So I have until 11. Is that enough time for you?
Yeah. I mean, we could just, generally talk about it, and then Friday I'll come in and really have the question.
Okay, awesome. All right. So thank you, everyone else. Have a great spring break, and I'll see you in a couple of weeks. And then Sebastian, you and I can just stay online for a bit.